Okay, so what I wanted to do is go through some of the pieces of the lab that we worked on in class the other day. And I kind of designed this because I really felt that there was kind of a large need after receiving all the emails. And so, kind of my goal through what I'm doing this evening, using my not full equipment, just what I have with me on the trip, I want to go through and kind of identify the basics of this lab experience. So here goes like the actual data for this lab. So first of all, I want to look over here at this picture that I have right over here. So I just made a mark on it. So this was the setup we had. We had the plant through rubber tubing. You see the rubber tubing right through there. And then we also had this like calibrated pipette, it says right through here. So that calibrated pipette actually has a total of 1 milliliter. And so I just feel like really compelled to make sure that we're good on understanding the nature of that pipette. So about right at this point, somewhere towards the top, it said 0. And down towards the bottom, it said 1. So that means that in the region that we have in between those, so if you will, this region that I've shaded in like with yellow color, that volume in that yellow region is accounting for like 1 milliliter of water. So that's how the tube works. Now, we'll come back to the tube in a second, but looking back over here at our actual entire transpirometer, or it's called potometer, what we can see is that the nature is that transpiration, which I wrote down here in this picture, I just put an X by it, CO2 goes in the leaf, but out of the leaf comes water and O2. So plants take in CO2 and they release O2. Well, that's the nature of photosynthesis. But we need to talk about that loss of water. Well, that's what transpiration is. It's pretty much the loss of H2O through these little openings here called the stomata. And so that stomata is the site at which water is lost. That loss of water is called transpiration. So the way that this would work is that if water is lost through the leaf, so if water moves that way and if water moves this way, then that means that the amount of water in this tube should go down over the course of time. Now, I will tell you that the amount it will go down cannot be above 1 milliliter. There was not a single group that I saw in the 9 years I've taught this class where their water level went from the top all the way to the bottom. It just wouldn't happen. Not in the amount of time we had. Most groups didn't start at 0 either. Honestly, a lot of groups started somewhere right through here, like, I don't know, 0.21 milliliters. And that's okay. So in other words, to say everyone started at 0, that's like almost impossible because who can get the water level exactly at 0? I think I set up several lab groups and I had one group the other day where it started out at 0. So that's the nature of that. So to make sure we're good at seeing this, before we move into the next phase of like my drawing, we're talking about the lab. We're looking at a potometer, and we've identified the potometer as the actual structure that studies the rates of transpiration in a plant. That transpiration, which is the loss of water, I wrote that out earlier, that loss of water happens on these little holes, which you can see in my picture below here, bunch of little stomata openings on leaves right in this region right through there. There's one stomata and there's a second stomata, and all these stomata are where you would find, as we mentioned earlier, this exceedingly large and extreme loss of water. And so that loss of water we identified earlier is something that happens naturally through a plant. And so our potometer studied that, and we used this pipette, which you can look at my right-hand drawing that I'm using, or right-hand illustration. We used a setup that was like essentially this one right through there. So that setup that I just put an X on is what we had in class. That is very close to, that's very close to what we had available to us. So do that, undo that, undo that, undo that. And as a reminder, the way the water moved is the water moved literally this direction. I'm sorry, I wrote that wrong. It moved this direction because the water leaves out the leaf. So that is the nature of water loss through transpiration. Okay, so that takes care of that. So why are we running this lab? Well, the question is, what environment elicits or causes there to be a more extreme loss of water? So in other words, where would we expect to find lots of water loss? Where, as I phrased it, so where would transpiration rates be the highest? Is it in the environment that we have here? That was the desert right there. Is it a hurricane environment, or is it a rainforest? Is it the tundra? Is it an area where there's just a lot of wind, or is it maybe in Mr. Field's classroom where your rate of transpiration is the highest? Now, this to me is where things started to kind of fall apart, because then we had to have that environmental design. And I thought everyone's design was fine. The way that you engineered your desert or you engineered your windy environment, there wasn't a problem with that. I think it was more along the lines of how did we account for the data? So I want to look at this region right here and below. I want to talk about the nature of this data. Now, we know that along the course of time, I had called each group over to the board, and I said, let's talk about these steps that are right through here. And so I went through the steps. Now, since everyone I hope is watching, here are the steps. We took a box that was 1 centimeter by 1 centimeter of a leaf, and we cut it out. There was a ruler there. Now, I would think that my experience has been that the mass of that 1 centimeter section of the leaf, that 1 centimeter section of the leaf is generally about 0.01 or so grams. That's the mass of that section. Now, with that in mind, then we took all of the leaves off and we put all of the leaves on our balance. So at first we took just the little one section and we put it on the balance, and it said something like 0.01 grams. And then we put all the leaves on the balance. And then let's say that it had said 530 grams, because in the lab that I did, I think it was in and around, it was over 530 grams that I had, but I was using a ivy with thick leaves, and there were a lot of them. So 530 grams. So what do we do mathematically to get some of these numbers? So pay close attention. I have done step one. I have cut out the 1 centimeter section of a leaf, and I massed it to be 0.01 grams. And so I've massed it too. Then I multiply that by 10,000. So 0.01 times 10,000 comes out to be, and this is where we'll get out our little calculator, and I'm literally taking my iPhone and using a 4-function baby calculator on it. 0.01 times 10K comes out to be 100. So that's 100. So that's getting me through this point right there. Divide the total mass of leaves, which I got is 530. Divide that by, it says the mass per square meter, which is that number 100. So divide that by 100 and you get 5.3. That says this is the value of the leaf surface area. Record this in your lab write-up. So that 5.3 value is something we need to account for and keep track of, because when it's time for us to actually run through some of our data and get this massive chart, which you saw me get, we actually have to do some math to get that. So let me show you some of the math that we would need to do to ultimately get this table. So what we have is we've identified that our value coming from this step right through here is step through there was something along the lines of, it was 5.3. So we get 5.3. Now, our reading on our protometer is dependent upon whatever it was in your glass tube. I had said in the prior section when I was in the other picture that most groups didn't start at 0. Most didn't start at 0 at all. I had even said that a lot of groups started maybe perhaps somewhere like around that 0.21 milliliters. So let's say that that was the case. So what if this was 0.21 milliliters? Well, at the 30-minute mark, let's say that it went down some more. So let's say maybe it was like 0.24. So I'll write that in there, 0.24. Went down a little bit. And maybe at the 6-minute mark, it was like 0.25. Didn't change that much at all. Maybe it's 0.25 there, 0.29, 0.31, 0.33. And I'm going to stop there because you get the idea of what's going on. So the water level didn't change that much over the course of the 18 minutes. In fact, if you do the subtraction between 0.33 and then the 0.21, over the course of that 18-minute time frame, it changed like 0.12 milliliters. So how much loss of water was there at time 0? Well, clearly there were 0 milliliters because you had no water loss. But then how about at 3? And this is where we got to just make sure we're good because this is cumulative water loss. And so at the 3rd minute, you're at 0.24 milliliters, so you've lost 0.03 milliliters of water. Well, then I want you to think about it. What would the value be at this box for 6? The answer would be 0.04 milliliters. Why? Because it's 0.25 now at the 6th minute, but it was originally 0.21. Do not write 0.01 milliliters. That is wrong. I noticed a lot of people were taking like the change of volume there. That is not correct. It's got to be volume change over the course of time. So what would it be here? Well, it still would be 0.04 milliliters there. How about at 12? So 0.08 milliliters. At 15, 0.1 milliliter. And then at 18 minutes, it's 0.12 milliliter. Now, how do we normalize this per meter squared? Well, this point right here is where you divide your water loss, which in this case is 0, divided by the value we got from doing this math right here. So that's 0 divided by 5.3. That's clearly equal to 0. So what would 0.03 divided by 5.3 be? Well, take out my calculator. So it was 0.03 divided by 5.3, 0.0057. So equals 0.0057. Now, if we're looking for unit, this is milliliters lost per meter square. Amount of water loss per meter square of leaf. For this next one, it would be 0.04 divided by 5.3, which comes out to be 0.04 divided by 5.3 is 0.0075. 0.0075 milliliters per meter squared. And let's jump to the 18-minute mark. So that would be 0.12 divided by 5.3, which comes out to be 0.12 divided by 5.3. So what do we get there? 0.12 divided by 5.3, 0.022. Okay, so there is the data I have. And of course, these boxes will get filled in as well. And I'm honestly making this data up as I go along because this is not the true data. I will say, though, that this data is actually from when I ran the lab on a grandiose scale several years ago, and tested out all these different environments to make sure that the lab worked. So this data, in a way, is like the manifestation of taking data of that nature. And you can kind of see the numbers in and around, they match up. So make sure you're good at doing like this. I want you to be set on the nature of this like lab. So hopefully you're good on that so far. A couple thoughts about this. One is that when this lab was run with a unique species of plant. It actually wasn't an ivy at all, and the amount of leaves were actually like fairly great as far as like the number of leaves, and they actually were naturally pretty big leaves. So that's why my leaf surface area was actually quite large. Y'all's is significantly smaller in your data set. This should be a number that's probably much less than one, I would suspect. The amount of water loss is very unique per plant, but I felt like most groups were having water loss of like from beginning 0 to the end at 21 minutes. They were having like zero point 0.2 milliliters at most being lost, like 0.20 milliliters total that was lost. Your story is your story. Your lab is your lab, and my species of plant that I was using was different than your species of plant, and the scale. Y'all could maybe perhaps like your potometer setup was smaller than mine. In the end, the data is the data. It's more about the relationship though that's important. And so to kind of conclude this, let me go back to this. Uh, there's that data, and that's on the front of the website. This is not, though, and this was a graph made so very quickly, and this is not clearly labeled, and I understand that. It's just so that I had something to kind of gravitate towards. So there's time on your x-axis, and I've taken this up to 30 minutes. Different colors, different environments, and then over here on my y-axis is the amount of transpiration. And so it seems like in the case of like the green dot, there was larger transpiration over the course of time. For the purple dot, there was like minimal transpiration over the course of time. Well, so that means in the hurricane environment, there wasn't a lot of water loss, and neither was there in the rainforest, but there was in the desert. And let's see, for the baby blue, so that was the desert. There was another desert there. What was the dark blue one? Tundra. So tundra and desert had some pretty extreme water loss, not so much rainforest and not so much in the hurricane environment. Now, last concluding thought, and then I'll be done. The nature of water, just so that we're good in understanding this principle, so that we know why the data happened as it did, is that water goes to where water is not. Now, I want us to think about a rainforest environment. So let's say that this green structure is a leaf. This is like crude drawing, best I can do without my actual like real setup here. Okay, so there's the leaf. The way that water moves is water moves out of the leaf through those stomata. But what if I said the leaf was already immersed in so many ways in water? So if the leaf was already immersed in water, what does that mean? Well, oops, I didn't mean to do that. So if it was immersed in water, I guess maybe I could have done that. Could have done connection there. Great. So if it was immersed in water, let's see if this works. Yay. Okay, so there's my leaf. It's now immersed in water. Well, water moves to where water's not, so I don't think this plant would lose any water at all because there's a ton of water on the outside of it. But what about a plant that's in the desert? Well, a desert's more like this. See, there's no water around. In the case of the desert, it seems like lots of water would be lost because honestly, in the case of a desert, the water is actually in the leaf. There's no water on the outside. So the desert should have lots of water loss, but if you think about it like underwater, clearly this is underwater, or in a way, rainforest or highly humid environments, like they would cause this pretty much. And in high humid and in high wet environments, like a hurricane or a rainforest, there is no compelling force that moves water out of the leaf. And so the rate of transpiration should be low in those environments. So I hope that's made a difference. The data is on the front page of the website. Your group needs to still have good data. And I want to make sure that we're 100% clear on that the expectation is that you're supposed to run the lab, get good data, and when it's a little off, figure out why. The nature of this is that the numbers should all be in and around the same because you all got in and around the same type of plant. You all had ivy. That's why I told you get ivy. So your numbers could be much different than mine, but every group is going to be in and around the same, and I hope that makes sense. The species of plant I used resulted in these very low transpiration rate numbers. The species of plant that y'all used, or the genus of plant that y'all used, this ivy family that you were using, they should all have around the same numbers. So if we have a group that has very low values and then a group that has like 100s, there's one of the two is wrong, like very clearly. make sure that you are doing the math correctly. If you need help with that, literally think about how I ran this section right through there, and make sure that you've set it up the right way. And maybe some groups have and some groups haven't. It seems like that's probably the case because the data just they're too different. Everyone's data should be kind of in and around the same, and what it should be is that when we graph it, it should be kind of like this graph. I feel like right now though, there are some people that have like 100. Oops, they have like 100 is their value for transpiration, and there's some that have like zero point 0 something. We need to all get on the same page with that. So please make sure that you are checking your data appropriately. If you have questions, shoot me an email. Good luck.